Space is not an emptiness, it is an ocean, a boundless sea of spacetime, stretching in every direction, without shore, without horizon. In this ocean, matter drifts like islands, stars flare like lighthouses, and galaxies swirl like great archipelagos of fire. Yet, in the heart of this cosmic sea, there are places where the current folds inward, places where reality itself spirals down into silence. These are the whirlpools of existence, black holes, regions where gravity becomes so absolute that not even light can escape, where space collapses and time itself loses meaning. They are both real and unreal, visible only in what they devour, and yet their presence shapes galaxies, bends starlight, and sculpts the very architecture of the universe. For centuries they were whispers, shadows on equations, dismissed as curiosities. Today they are no longer myth but measured fact. Telescopes have seen their shadows. Detectors have heard their collisions reverberate through spacetime. And yet, though we know they exist, we do not know what they are, what lies at their center. A singularity, a point of infinite density, where the known laws of physics collapse into silence. Is this the end of matter, the death of time, or the beginning of something hidden beyond our comprehension? Is the singularity a wound in the fabric of reality, or the seed of new worlds? The whirlpool at the center of reality is not just a riddle of physics. It is a mirror reflecting our deepest hunger to know, to ask, when space falls in on itself, when time spirals into darkness, does reality end, or does it begin again? The story of the whirlpool begins not with telescopes or satellites, but with an idea, a whisper carried through equations long before any human eye could witness its truth. For centuries, gravity was thought of as a gentle tether, binding planets to their orbits, moons to their hosts, and apples to the earth. Isaac Newton described it as a force, invisible yet universal, stretching across infinite space. In Newton's cosmos, the universe was eternal, absolute, and unbroken, and yet, even in the 18th century, some minds dared to imagine something darker, hidden within Newton's framework. John Mitchell, an English natural philosopher, pondered, what might happen if a star was so massive, and its gravity so strong, that not even light could escape its pull? He called them dark stars, bodies that might exist invisibly, detectable only by their unseen influence. Almost in parallel, the French mathematician Pierre-Simon Laplace arrived at a similar speculation, suggesting that such objects could vanish from view, swallowing their own light. To their contemporaries, these ideas bordered on fantasy, curious thought experiments, but far removed from the visible order of the heavens. The centuries turned, and physics evolved. In 1915, Albert Einstein unveiled his general theory of relativity, a vision of gravity not as a force, but as the curvature of spacetime itself. Space and time were no longer separate. They were woven into a single fabric, capable of bending, warping, and twisting beneath the weight of matter. Planets orbited not because they were pulled, but because they followed the curves of this cosmic geometry. Within months of Einstein's revelation, Karl Schwarzschild, a German physicist serving on the Eastern Front during World War I, solved the equations of relativity for a single, perfectly spherical mass. His solution described a strange boundary, a point beyond which space-time curved so extremely that nothing, not even light, could return. In essence, Schwarzschild had mathematically uncovered the first true black hole. Yet at the time, it was dismissed as a mathematical oddity, a solution too extreme to exist in the physical universe. For decades, singularities and event horizons lingered as shadows at the edge of physics. Even Einstein himself resisted the notion that such objects could form in reality. They seemed to defy reason, to mock the stability of nature. The idea that stars could collapse into bottomless voids, leaving behind no trace but their gravitational presence, was too radical for many to accept. But the universe had other plans. In the 1930s, Subrahmanyan Chandrasekhar, a brilliant young astrophysicist, calculated the fate of stars at the end of their lives. He discovered that beyond a certain mass limit, now called the Chandrasekhar limit, stars could not hold themselves against gravity's inward pull. For lighter stars, collapse ended in the quiet ashes of white dwarfs. For heavier ones, neutron stars could form, dense as atomic nuclei. But for the most massive, no pressure could withstand collapse. They would implode endlessly, vanishing into regions of infinite density. At first, his ideas were dismissed, most famously by Arthur Eddington, who resisted the notion of nature going so absurd. Yet time proved Chandrasekhar correct. Stellar evolution demanded an ending more violent, more mysterious than anyone had foreseen. By the mid-20th century, the universe began revealing its darkest secrets. Astronomers detected quasars, astonishingly bright, distant beacons, outshining entire galaxies. Their energy defied explanation, until it became clear that only matter falling into supermassive black holes could power such cosmic lighthouses. These were not mathematical curiosities. They were engines at the hearts of galaxies, visible across billions of light-years. In the decades that followed, evidence mounted. X-ray astronomy revealed binaries in which invisible companions pulled gas from neighboring stars, heating it to millions of degrees in whirling disks before it vanished across unseen horizons. Observations of stellar orbits in our own galaxy showed stars whipping around an invisible core, the unmistakable footprint of a black hole, millions of times the mass of the Sun, and yet the definitive proof remained out of reach. Black holes are invisible by definition. They swallow their own light. They announce themselves only through the chaos around them, like whirlpools seen not directly, but in the spirals they carve into the ocean surface. The turning point came in April 2019, after decades of planning. A global array of radio telescopes known as the Event Horizon telescope released the first image of a black hole's shadow, a glowing ring of matter swirling around the dark heart of the galaxy M87. It was not an artist's impression, nor a simulation. It was real. Humanity had, for the first time, gazed into the whirlpool itself. In that blurred, golden ring lay the culmination of centuries of speculation. What Mitchell and Laplace had dreamed in whispers of dark stars, what Schwarzschild had unearthed in the trenches of war, what Einstein had doubted, what Chandrasekhar had calculated, what quasar light had hinted, was now undeniable. Black holes were not figments of mathematics. They were monuments of nature, sculpted by gravity into regions where reality itself turns inward. And yet, even as their existence was confirmed, their mystery only deepened. Scientists such as Roger Penrose and Stephen Hawking showed that singularities, points where density becomes infinite, were not artifacts of imperfect equations, but unavoidable consequences of relativity. These whirlpools were not just curiosities. They were the places where the known laws of physics ended. To look into a black hole is to look into the limit of understanding, into the silence where theories dissolve. And in that silence, one question lingers: what lies beyond? The horizon. From Newton's falling apple to the shadow cast by M87, humanity has slowly traced the outlines of this abyss. Each generation of thinkers has carried the torch further. From speculative dark stars to mathematical singularities, from quasars to the first image of the unseeable, the whirlpool at the center of reality has emerged from myth into measurement. Yet, its center, the place where space collapses, where time ceases to flow, remains hidden. What began as a discovery has now become a challenge. The whirlpool is no longer just an object in the universe. It is a frontier of truth, waiting, silent, pulling us inward. The discovery of black holes as real, physical entities marked not only a triumph of science, but also a shattering of its confidence. For in confirming their existence, physicists were forced to admit that these whirlpools of spacetime do not simply challenge human imagination. They dismantle the very foundations upon which science rests. At the heart of every black hole lies a singularity, a point where matter is compressed to infinite density, where volume shrinks to nothing, and where the equations of general relativity surrender to silence. Infinity, in physics, is not a solution but a signal of collapse, a flashing warning that the theory has reached the end of its power. The singularity is not simply unknown. It is unknowable, at least within the language of current physics. This was the shock. Relativity, the most successful description of gravity ever written, could predict black holes with exquisite precision. It could describe how light bends near them, how time slows at their edge, how stars orbit in their thrall. Yet, at the very center, the theory collapsed. Here, the smooth fabric of spacetime, stretched and curved by mass, was torn apart. To admit black holes was to admit that Einstein's great masterpiece carried within it the seed of its own incompleteness. The event horizon sharpened this terror. It is not a physical surface, not a wall or barrier, but a point of no return. A photon born just inside the horizon is doomed to spiral inward forever, never reaching the outside universe. A traveler crossing it would not notice the instant. Yet to the external cosmos, they would appear frozen at the edge, time itself slowing to a halt. To speak of horizons is to speak of reality dividing into two irreconcilable views. One falling inward, one watching from outside. Both true, both contradictory. The strangeness deepens when one considers what happens to matter at the brink. As an object approaches a black hole, gravity stretches it along its length while compressing it sideways, an effect known as spaghettification. A star venturing too close can be torn apart, its gases spiraling in luminous streams into the accretion. Disk, entire suns, devoured not in silence but in radiant violence, become fuel for the whirlpool. In these final acts of destruction, black holes light the universe in quasars so bright they can outshine galaxies. The paradox is brutal. The darkest objects in the cosmos are revealed by their brilliance. Yet perhaps the greatest wound black holes dealt to physics came not from relativity, but from quantum theory. In the 1970s, Stephen Hawking demonstrated that black holes cannot remain entirely black. Through subtle quantum effects at the horizon, they must emit radiation. Over immense timescales, this Hawking radiation allows them to evaporate slowly, leaking away mass until they vanish entirely. This discovery stunned the scientific world, for it suggested that black holes are not eternal. They die, but in their death arose an even deeper crisis. If a black hole evaporates completely, what happens to the information it once consumed. In quantum mechanics, information, the description of a system's state, can never be destroyed. It may transform, scatter, or become inaccessible, but it must endure. Yet in Hawking's formulation, the evaporation of a black hole seemed to erase information forever. This was the infamous information paradox, a direct contradiction between the two great pillars of modern physics. Relativity allowed the black hole. Quantum theory demanded its laws remain inviolate. Both could not be true as written. Here lay the scientific shock in its purest form. Black holes were not just exotic objects at the edge of galaxies. They were contradictions made flesh. They embodied the rift between the very theories that defined 20th century physics. To study them was not to refine equations, but to stand before a fracture in the edifice of knowledge itself. Hawking's work, alongside Roger Penrose's singularity theorems, proved that the paradox was not an illusion. If relativity is correct, singularities must form. If quantum theory is correct, information must survive. Yet within a black hole, both demands collide. Reality itself appeared to demand reconciliation. A new theory, one beyond Einstein and beyond quantum mechanics. A bridge across the abyss. The emotional weight of this realization was profound. For centuries, science had advanced by peeling back mysteries, turning questions into certainties. Yet here was a phenomenon that not only resisted explanation, but revealed the very tools of explanation as incomplete. Black holes were not mere puzzles to be solved. They were mirrors held up to physics, showing its limitations, exposing its fragility. And still, the paradoxes multiplied. Time itself bent to absurd extremes near the horizon. For an outside observer, the fall of matter into a black hole appeared to freeze, never quite completing. Yet for the infalling matter, the plunge continued inexorably to the singularity, whose clock was true. The relativistic answer, both. But how can two mutually exclusive realities coexist? In this dissonance, black holes became more than astrophysical entities. They became laboratories of thought, crucibles where the deepest assumptions of science are tested and broken. They are places where entropy, information, energy, and geometry intertwine in ways unseen anywhere else in the cosmos, and with them came terror. For if information can vanish, then determinism, the very idea that the universe unfolds according to knowable laws, collapses. If singularities exist, then the predictive power of relativity dissolves. If event horizons are truly impassable, then parts of the universe are forever cut off from knowledge. In black holes, the dream of total understanding gives way to a new truth, that some horizons cannot be crossed, some answers cannot be known. This was the scientific shock, the moment when humanity realized that the whirlpools at the center of galaxies were also whirlpools at the center of knowledge. They dragged not only matter and light into their depths, but also certainty, order, and confidence. They forced science to admit what it had long resisted, that the universe is stranger, more fragile, and more elusive than even its boldest theories had imagined. And yet, in that shock lay the seed of something greater. For in confronting the abyss, physics glimpsed its next frontier. Black holes revealed the need for a deeper synthesis, a unification of relativity and quantum theory, a framework that could explain both the curvature of spacetime and the whisper of particles. They became not the end of inquiry, but its most urgent beginning. The whirlpool at the center of reality was no longer just a feature of galaxies. It had become the crucible of truth itself. the place where science admitted its own incompleteness, and in doing so, set the stage for the next great transformation of knowledge. The shock of black holes did not end in theory. Once the equations had declared their inevitability, once Hawking and Penrose had stripped away the illusion that they were only mathematical curiosities, the cosmos itself began to reveal them. The deeper the eyes of science peered into the night, the more the whirlpools showed themselves, vast, voracious, undeniable. The instruments of this investigation were as diverse as the mysteries they pursued. Radio telescopes stretched across continents, gathering faint whispers from distant galaxies. X-ray satellites orbited Earth, listening for the violent signatures of matter heated to millions of degrees as it spiraled into a black hole's embrace. And, in a feat unimagined only decades earlier, detectors built to measure distortions in spacetime itself began to register the echoes of collisions between black holes, waves rippling outward from their violent unions. Each tool revealed a different facet of the enigma. Radio astronomy, pioneered in the mid-20th century, first stumbled upon quasars, quasi-stellar objects that shone with an intensity that defied reason. Some blazed with the light of 1 trillion suns, yet appeared no larger than a star through optical telescopes. The only engine powerful enough to explain such brilliance was the infall of matter into a supermassive black hole, its gravitational energy transformed into radiation. With quasars, the existence of giant black holes was no longer speculation. They were not rare monsters, but central engines, dwelling in the hearts of galaxies. X-ray astronomy added further detail. Satellites like Uhuru, Chandra, and XMM Newton revealed binary systems in which one star orbited a collapsed companion. Gas stripped from the living star formed an accretion disk around the unseen partner, heated to such extremes that it glowed in When the mass of the invisible companion was calculated, it exceeded the threshold for neutron stars. The verdict was unavoidable. These were stellar mass black holes, the graves of once massive suns. The cosmos had seeded them everywhere, hidden in binaries, cloaked in silence until their hunger betrayed them. But perhaps the most profound revelations came not from light at all, but from the trembling of spacetime. In 2015, the Laser Interferometer Gravitational Wave Observatory (LIGO) captured a signal that lasted less than half a second, a faint chirp, a tiny oscillation in its laser beams. It was the signature of two black holes merging over 1 billion light-years away, their collision releasing more energy in gravitational waves than all the stars of the universe emit in light. The detection confirmed Einstein's century-old prediction that space-time itself could ripple. It also proved that black holes could not only exist, but dance, collide, and reshape the cosmos in their unions. The deeper investigation did not merely confirm black holes. It began to chart their behaviors. Computer simulations, powered by numerical relativity, modeled what human eyes could never see: the spirals of stars torn apart, the orbits of gas in turbulent disks, the formation of jets that speared outward at near light speed. In these digital laboratories, physicists could watch space fold and twist, time stretch and fracture, and matter obeyed laws that bordered on the surreal. It was in these studies that black holes revealed themselves not as silent voids, but as engines of order and chaos alike. Their accretion disks radiated more energy than nuclear fusion, lighting galaxies across billions of light-years. Their jets pierced intergalactic space, seeding regions with magnetic fields and influencing the birth of stars. Far from being passive consumers, black holes emerged as architects regulating the growth of galaxies, shaping the large-scale structure of the universe. Yet, for all their grandeur, the paradoxes deepened. The investigation of black holes forced scientists to reconsider fundamental laws of nature. In the 1970s, Jacob Bekenstein showed that black holes must possess entropy, a measure of disorder, proportional not to their volume, but to the surface area of their horizons. Hawking's radiation confirmed this, introducing a new branch of physics, black hole thermodynamics. The equations suggested a strange truth. The information content of a region of space may be encoded not within its volume, but on its boundary. This was the seed of the holographic principle, the idea that the universe itself might be a projection, a three-dimensional illusion encoded on a two-dimensional surface. Black holes, in their silence, had whispered a secret about reality itself. They were not edges of physics. They were its crucibles, places where quantum mechanics, relativity, and thermodynamics converged in unexpected harmony and violent contradiction. The deeper investigation also entered the realm of extremes. Could black holes be probed not only through their effects on stars and gas, but directly? In 2019, the Event Horizon Telescope, a network of radio dishes linked across the globe, achieved what had once been unimaginable. By combining observations with the precision of a planet-sized instrument, it captured the first image of a black hole's shadow in the galaxy M87. A glowing ring of matter, warped by gravity, encircled a dark center. It was not an artist's rendering, not a simulation, but a photograph of the whirlpool itself. The image confirmed Einstein's predictions to stunning accuracy. Yet it also deepened the awe. To look upon a black hole was to see a place where light itself bowed in surrender. Every layer of observation added more questions. The gravitational waves of LIGO revealed a population of black holes larger than expected, suggesting unknown processes in stellar death. The jets of quasars hinted at magnetic fields of astonishing strength, whose origins remained uncertain. The images of the Event Horizon Telescope showed turbulence and structure that theory had not fully explained. Each discovery confirmed the reality of black holes, but none diminished their mystery. Instead, they multiplied it. In laboratories on Earth, physicists probed further by pushing the frontiers of particle physics. At CERN's Large Hadron Collider, collisions recreated energies similar to those that once prevailed in the early universe. Some theorists speculated that microscopic black holes might be produced in these experiments, vanishing instantly in bursts of radiation. None have been detected, but the very possibility underscored how deeply black holes penetrate into fundamental physics. They are not merely astrophysical objects, but theoretical bridges to the smaller scales of existence. Quantum experiments, too, probed the paradoxes. Can information truly be lost in a black hole? Or must some hidden mechanism allow it to escape? Woven into Hawking radiation in ways not yet understood, physicists built thought experiments, constructed mathematical models, and tested holographic dualities that suggested information could indeed survive, yet no definitive proof emerged. The paradox remained, a riddle at the edge of comprehension. The deeper investigation revealed black holes as more than singular mysteries. They became crossroads where every branch of science converged: astronomy, particle physics, quantum theory, thermodynamics, relativity, and information theory. Each lens illuminated a piece of the whole, yet none resolved the singular center, where knowledge broke down, and through it all, An emotional undertone endured. To study black holes was to gaze into a mirror of the universe's extremes: creation and destruction, order and chaos, certainty and paradox. They embodied the fragility of knowledge, the resilience of inquiry, and the humility of a species daring to look into darkness and ask what lies beyond. The whirlpool at the center of reality had ceased to be hidden. It was photographed, measured, and heard in the tremors of space-time itself. Yet with every advance, the mystery deepened, for black holes revealed not simply themselves, but the unfinished nature of human understanding, the silence at the core of all knowledge. The deeper the instruments looked, the stranger the cosmos became. Black holes, once the distant curiosities of theory, revealed themselves as agents of order and disarray, architects of galaxies and assassins of certainty. Each new observation did not conclude the story. It opened another corridor, leading farther into paradox. At the core of the mystery stood the singularity, the unresolved center, where space-time ended and explanation failed. General relativity demanded its existence. Quantum mechanics refused to accept it. Between these two commands stretched a silence into which theory shouted and was answered only by echoes. The singularity was not merely a point of infinite density. It was a verdict that current knowledge was incomplete. Even to name it was to admit that the language of physics fell short where gravity grew absolute dot around that center. The event horizon traced a boundary both simple and terrible, a mathematical surface beyond which return was impossible. But the horizon itself became a battlefield for ideas. Hawking radiation implied that black holes evaporate, giving off a faint thermal glow. Bekenstein's entropy assigned them a measure of information proportional to their surface area, not their volume. Together, these truths demanded that the horizon know something about the interior. That surface area could carry the record of a volume's worth of states. The idea was unsettling and fertile. It hinted that the universe might encode itself holographically, that reality stores its deepest data on boundaries rather than in bulks. Yet the gift of insight came with a wound, the information paradox. If black holes radiate away and vanish, what becomes of the information carried by everything that fell in? Quantum theory insists that information is never truly destroyed. Hawking's original calculation suggested otherwise. For decades, the paradox split physics across a fault line. One theory or the other must bend. The stakes were absolute, not just for black holes, but for causality, determinism, and the coherence of physical law. Then came an escalation even bolder, the firewall paradox. If information must escape in Hawking radiation to preserve quantum unitarity, some argued, then the horizon cannot be innocent. It must seethe, must burn, must act as a barrier of high energy, quanta, a firewall, incinerating anything that crosses. But relativity's equivalence principle says a freely falling observer should find the horizon locally unremarkable. With no drama at all, the two claims cannot both be true. Either unitarity breaks or gently falling becomes impossible. The horizon, once thought to be a serene geometry, threatened to become a place of violent contradiction, while theory wrestled with horizons. Observation troubled the origins of the monsters themselves. Telescopes peered back to a time when the universe was scarcely a few 100 million years old and found quasars powered by black holes already weighing hundreds of millions, even billions of solar masses. How had such giants grown so quickly? Stars die to make stellar mass remnants. Accretion can fatten them, mergers can compound them, but the cosmic clock was tight. The existence of such early leviathans forced new scenarios: direct collapse of primordial gas into massive seeds, hyperefficient accretion that skirted theoretical limits, dense star clusters collapsing as one. None alone felt sufficient. Their very presence hinted that the birth of supermassive black holes was more radical than expected. The cosmic dawn was not a gentle sunrise, but a storm. The mystery deepened on galactic scales. Observations showed that the masses of central black holes correlate with the properties of the galaxies that host them, with the velocity dispersions of stars in their bulges, with the overall luminosity of those central regions. Somehow, an object smaller than a solar system knew the shape and fate of a structure 100,000 light-years across. Feedback from jets and winds offered a mechanism. As a black hole fed, it launched energy that heated and expelled gas, shutting down star formation and regulating a galaxy's growth. Yet the precision of the correlations continued to astonish, as if the whirlpool and the island that formed around it were co-authors of a single script. Even the void between galaxies bore their signatures. Relativistic jets stabbed intergalactic space, inflating cavities in hot gas, stirring magnetic fields that stretched for millions of light-years. The emptiest regions carried the fingerprints of the densest things. Black holes were not merely endpoints of collapse. They were gardeners of structure, pruning and seeding the cosmic web. Still, the contradictions multiplied. If black holes evaporate, then, in the final flicker of Hawking radiation, where does the record of everything consumed reside? If it is encoded in correlations among the outgoing quanta, can physics recover it in principle, or is it scrambled beyond reach? Holographic dualities, correspondences between gravity in a volume and quantum theories on its boundary, hinted that information does not die. The interior might be reconstructed from the exterior's quantum data, but these were bridges built of mathematics, not yet of experiment. The map grew elegant. The territory remained shadowed closer to the horizon. Simulations revealed turbulent disks with magnetic fields threading the plasma, launching jets through mechanisms that braided rotation and magnetism Blandford's and its kin. Yet the sense of control was an illusion. Small uncertainties in the plasma's microphysics produced large differences in jet power and structure. Observations by the Event Horizon Telescope of supermassive black holes showed polarization patterns that seemed to dance to a choreography not fully deciphered. The closer knowledge came, the more it saw its reflection blurred. Then came the question with the weight of fate. What is the role of black holes in the acceleration of the universe? Dark energy drives cosmic expansion apart at an ever-increasing pace. Some proposed that vacuum energy, the same quantity that might underpin Hawking radiation and quantum fields, links black holes to the very fuel of cosmic acceleration. Others suggested that the population of black holes, as they form and merge, could contribute to apparent acceleration through subtle averaging of spacetime curvature. The proposals were provocative, their evidence contested, yet the possibility lingered. The whirlpools that end stars might whisper to the expansion that carries galaxies away. On the smallest scales, speculation hovered over the threshold of detection. Could microscopic black holes have formed in the early universe, when densities were extreme? If so, might some survive as relics candidates for dark matter? Searches have placed strong limits on many mass ranges, but not all. The idea refuses to vanish, a ghost at the feast, reminding science that the invisible mass of the cosmos could, in part, be the bones of ancient collapses, Even causality felt the strain. Space-time solutions allowed for wormholes, tunnels connecting distant regions, sometimes stabilized by exotic fields, in theory. Could black holes hide throats that open elsewhere? Could singularities rebound as white holes, ejecting matter into other times or places? Most models demanded materials not observed and faced instability when quantum effects were included. But as metaphors, they persisted reminders that the topography of space-time is less a plane than a landscape of surprises. Amid all this, a quiet dread grew. Perhaps the singularity is not a place at all, but a process that erases questions. If the laws that define inquiry fail at the center, then a black hole encloses not only matter but meaning. The universe keeps a secret, and the secret is that some truths cannot be told within its current grammar. No telescope can see the singularity. No detector can feel it. It is an absence with consequences, and its shadow falls across every law that seeks completion. Yet the dread was matched by wonder. Black holes unified what had seemed separate. The physics of the smallest scales and the largest, the birth of stars and the fate of galaxies, the whisper of quanta and the shape of spacetime. They were paradox and synthesis at once, wounds through which deeper order bled into view. In the end, mystery did not recede. It changed form. The event horizon remained a boundary, but now it marked a frontier between rival descriptions of reality. The singularity held its silence, but its gravity informed everything around it. The brightness of disks, the violence of jets, the tremor of space-time, the arithmetic of entropy. The early universe offered giants too soon. The present universe held galaxies tuned by their central monsters. The future universe would fade under the governance of horizons, black, cosmic, an absolute dot. The whirlpool at the center of reality had grown from object to principle. It governed the birth of structure and the limits of law. Each answer opened a deeper question, each measurement a wider uncertainty. And still the pull persisted, a summons to think more bravely, to build sharper instruments, to risk new mathematics, to imagine a reconciliation not yet earned. The escalation was complete. Black holes no longer merely challenged understanding, they became the measure of it. When observation strikes against paradox, speculation rises to meet the fracture. Black holes became more than astrophysical curiosities. They became crucibles for ideas about the deepest architecture of reality. Each theory that attempted to tame them was less a conclusion than a poem written in mathematics, a vision of how the universe might weave its secrets. The most established framework was still Einstein's general relativity. Within its curved geometry, black holes emerged naturally, horizons where light bent back on itself, singularities where equations broke. Yet relativity was silent on the quantum grain of matter and energy, blind to the probabilistic breath of the microcosm. When it confronted singularities, it confessed defeat. Something beyond Einstein's triumph must be invoked. One pathway was loop quantum gravity, a theory that sought to quantize spacetime itself, breaking the smooth continuum into discrete loops of geometry. In this picture, singularities dissolve. Densities do not diverge to infinity, but rebound when they reach the smallest scales. A collapsing star might not end in a singularity, but in a bounce, perhaps spawning a new region of space-time, a white hole, or even another universe. Black holes, then, could be the wombs of creation, each collapse a seed of cosmos. The mathematics suggested it. The poetry of speculation embraced it. Yet without experimental anchor, It remained an idea suspended in conjecture. Another road was string theory, with its delicate filaments vibrating across hidden dimensions. String theory offered not just particles, but a framework where gravity and quantum mechanics could coexist. Within its scaffolding, black holes became laboratories for holographic dualities. According to the ADS-CFT correspondence, a black hole in a higher dimensional spacetime could be equivalent to a quantum system without gravity on its boundary. The holographic principle implied that every detail of a black hole's interior could be encoded on its horizon, that surfaces, not volumes, carried the truest ledger of reality. If so, the paradox of information was resolved not by destruction, but by translation. The universe itself might be a grand projection, its depth an illusion of encoded surface states. For some, this principle extended far beyond black holes. If spacetime could emerge from quantum entanglement, then geometry itself might be woven from the threads of information. Reality, in this vision, was not built of matter or fields alone, but of correlations, a fabric of connections from which the stage of space and time arose. Black holes, with their entropy tied to area, became proof that information is the deepest currency, more fundamental than atoms, photons, or even spacetime itself. Other speculations pointed toward wormholes, the Einstein-Rosen bridges first glimpsed in early relativity. Could the interior of a black hole lead elsewhere, another region of our universe, or even another cosmos entirely? In classical, general relativity, such throats pinched closed too quickly to permit passage. But in the realm of quantum theory, exotic matter with negative energy density might stabilize them. Some even proposed that entangled black holes could be linked by microscopic wormholes, a conjecture summarized in the phrase EOE equals EPR. Einstein-Rosen equals Einstein-Podolsky. Entanglement and geometry, wormholes and quantum bonds, might be facets of the same truth. Speculation turned stranger still with the idea of white holes, time-reversed black holes. Where a black hole absorbed everything, a white hole would expel matter, never allowing anything to enter. No evidence exists for such entities in the cosmos we observe. Yet, within certain mathematical frameworks, black hole evaporation could end not in disappearance, but in a white hole's eruption, the stored information reborn in a final release. Such visions were tenuous, but they suggested that collapse and explosion might be two aspects of a universal rhythm. Some theorists clung to the principle of cosmic censorship, the idea that nature always hides singularities behind horizons, shielding naked infinities from view. Yet numerical simulations suggested that in exotic conditions, collapse might expose a singularity directly, a naked singularity laid bare to the universe. If such objects existed, determinism itself could fracture, since without horizons, the future could no longer be predicted by initial conditions. Reality's script would become improvisation. Cosmic censorship remained unproven, a rule perhaps enforced, perhaps ignored, by the deeper grammar of quantum gravity. And then came the most radical speculations, that black holes might be bridges not just within the universe, but between universes. In some models of eternal inflation, the multiverse bubbles with endlessly birthing regions, each with its own physical constants. A collapsing star in one universe might tunnel through to spark the inflation of another. If true, the interior of every black hole could be a seed of cosmos, unreachable to us, but fertile beyond imagining. The whirlpool at the center of reality might not end the story. It might begin countless others, Philosophers of physics extended these ideas further still. If the holographic principle was right, and reality was fundamentally encoded in information, then perhaps the universe itself was a kind of computation. The laws of physics became algorithms, the cosmos a processor, black holes the ultimate hard drives where information was stored and scrambled. The idea resonated with the simulation hypothesis, a speculative but haunting question. If the universe is information, could it itself be a simulation? A dream calculated on some deeper substrate of existence? Black holes, then, would be debug logs of reality, artifacts revealing the architecture of the code. Amid such visions, caution endured. Each theory carried both power and fragility. Loop quantum gravity offered bounces but lacked unifying breadth. String theory wove holography but awaited empirical proof. Wormholes and white holes shimmered as metaphors more than confirmed entities. Cosmic censorship remained unresolved. The multiverse offered explanations at the cost of testability, and yet each vision pushed physics beyond despair. The singularity was not merely a place of silence. It was a challenge, daring science to invent a language capable of describing it. At the edge of certainty, even time itself trembled. Was the singularity the end of temporal flow, or the junction to other branches? Did the horizon truly erase the past, or did it fold the past into future states in ways no classical mind could decipher? Some cosmologists speculated that the Big Bang and black holes were mirrors, both singularities, one expansive, one contractive, perhaps joined in ways unseen. The whirlpool and the explosion, collapse and birth, might be twins. In this wilderness of speculation, black holes assumed a new role. They were not only astrophysical phenomena or solutions to Einstein's equations. They were gateways for imagination, forcing physics to contemplate its own incompleteness. They served as a testing ground where relativity, quantum mechanics, thermodynamics, and information theory converged. Where they clashed, new ideas were born. The paradoxes remained unsolved. No telescope could peer past the event horizon. No detector could penetrate the singularity. Yet mathematics opened pathways, and philosophy widened the view. Whether through discrete loops of geometry, vibrating strings across hidden dimensions, holographic encodings, wormholes, white holes, or multiversal births, each speculation sought to bridge the rift between what we know and what we yearn to know. In the end, speculation was not weakness, it was courage. The refusal to accept silence as the final answer. The whirlpool at the center of reality pulled not only matter, but thought. It drew equations, conjectures, metaphors, and dreams into its gravity. Each orbit around the mystery brought physicists closer to unity, even if the singularity itself remained untouchable, and so black holes became the stage where the next great theory might emerge. Whether the solution lies in loops or strings, in holograms or multiverses, no one yet knows. But all agree the key to reconciling gravity with quantum mechanics, the key to understanding the deepest structure of reality, may be hidden in the silence beyond the horizon. The whirlpool waits. Its darkness is filled not with emptiness, but with the bright fire of speculation. The whirlpool at the center of reality resists direct touch. No probe can cross an event horizon and return. No instrument can penetrate the singularity's silence, and yet science has not retreated. Instead, it has crafted tools subtle enough to skirt the edge, to read the shadows, the echoes, the ripples. In the absence of direct vision, humanity listens to the way spacetime trembles when black holes stir. The Event Horizon Telescope (ET) was one of the most audacious attempts to see the unseen by linking radio dishes across the Earth into a planet-sized interferometer. The EHT sharpened its resolution to the equivalent of discerning an orange on the surface of the Moon. In 2019, it captured the first image of a black hole's shadow, a glowing ring around the darkness at the heart of galaxy M87. That blurred halo was not simply a triumph of technology. It was proof that relativity's predictions held under extreme gravity. Future upgrades aim to make this shadow clearer, to transform still images into movies of plasma swirling, of space itself whirling. Each frame will test Einstein's theory against nature's handwriting. Yet light is not the only messenger. The universe speaks also in gravity itself. In 2015, the Laser Interferometer Gravitational Wave Observatory LIGO caught a ripple in spacetime, the echo of two black holes colliding over 1 billion light-years away. It was the faintest stretching of distance ever measured, less than 1,000th the width of a proton, yet it carried a story of unimaginable violence. Since then, LIGO and its European counterpart Virgo have catalogued dozens of mergers, with more awaiting discovery. Each collision is both confirmation and question. The masses are sometimes heavier than expected, the spins sometimes strange, the origins still debated. Gravitational wave astronomy has entered its golden age, and black holes are its brightest heralds. Soon, the listening will extend to space. The Laser Interferometer Space Antenna LISA, scheduled for the 2030s, will float millions of kilometers apart, its arms stretched across the void. It will be able to hear the deep, slow waves of supermassive black holes spiraling together, waves too long for earthbound detectors. With LISA, humanity will listen to mergers that shake entire galaxies, to whispers from the earliest epochs of cosmic history. If supermassive black holes formed unexpectedly early, LISA may reveal how other instruments focus on light that cannot be seen with human eyes. X-ray observatories, such as NASA's Chandra and ESA's XMM Newton, watch the hot plasma swirling in accretion disks just outside horizons. They reveal matter heated to tens of millions of degrees, atoms stripped bare, magnetic fields twisted and unleashed as jets shooting thousands of light-years. Future missions, like Athena, the Advanced Telescope for High-Energy Astrophysics, will probe these disks with unprecedented detail, mapping turbulence, watching space-time drag matter into spirals predicted by relativity. Radio arrays, like LOFA and the upcoming Square Kilometer Array SCAR, will survey black hole jets across the cosmos, tracing their influence on galaxies. Observations suggest that jets from supermassive black holes regulate star formation, either igniting or extinguishing it. Thus, the tools of radio astronomy link whirlpools to the evolution of galaxies, showing that what happens at horizons echoes across millions of light-years. Yet astronomy is not the only frontier. Particle colliders, such as the Large Hadron Collider LHC, seek hints of the physics that black holes demand, unification of gravity with quantum mechanics. Some speculative models suggest that at energies far higher than currently accessible, microscopic black holes could form, evaporating instantly via Hawking radiation. While such events have not been seen, the search continues, for their discovery would bind the cosmic and the quantum in one experiment. Elsewhere, quantum experiments test the foundations of information. Entanglement studies probe whether correlations can mimic the strange equivalences proposed in holographic duality. quantum simulators attempt to recreate analog black holes in laboratories. Bose-Einstein condensates, where sound waves mimic horizons, or optical systems where light behaves as if trapped. In 2010, a team claimed to detect analog Hawking radiation in such a setup, not proof, but a hint that the paradoxes of black holes might be accessible in earthly laboratories. Cosmic surveys also contribute. Maps of large-scale structure. The filaments of galaxies stretched across billions of light-years constrain how black holes may influence cosmic evolution. If primordial black holes formed in the early universe, some fraction could survive today as dark matter candidates. Microlensing surveys search for their signatures, while gravitational wave data places limits on their abundance. Each test sharpens the boundary between speculation and possibility. Even Earth itself catches fragments of black hole physics. Cosmic rays bombard the atmosphere, neutrinos ghost through detectors buried in ice, and satellites record gamma-ray bursts. Some of these phenomena may involve black holes, the collapse of massive stars, the feeding of quasars, the eruption of magnetized jets. Instruments like IceCube and the Fermi Gamma-Ray Space Telescope provide indirect glimpses, each observation a puzzle piece. The collaboration between mathematics and experiment grows ever tighter. Numerical relativity, powered by supercomputers, simulates black hole mergers, predicting waveforms that detectors now confirm. Theoretical collaborations, exploring holographic principles and quantum gravity, refine the questions that telescopes and detectors might answer. In this dance, theory and observation orbit one another, both pulled toward the unseen center. The next decade's promise deeper revelations. The EHT's expansion to include more antennas will yield sharper movies of horizons. LISA will open a new frequency band in the cosmic symphony of gravity. Athena and Lynx will probe X-ray whispers of infalling matter. SKA will map the feedback of jets across cosmic history, and quantum laboratories will continue to push analog horizons to their limits, seeking patterns that echo those of cosmic black holes. Through all these tools, science is not merely observing black holes. It is probing the seams of reality, for black holes are not just astrophysical bodies. They are crucibles where relativity, quantum mechanics, and thermodynamics collide. They are experiments the universe has already run, awaiting our instruments to interpret. Each shadow imaged, each ripple detected, each spectrum mapped is more than data. It is a clue to the grammar of existence, a whisper of how reality itself is woven, and yet humility endures. These tools approach but never touch the horizon. They glimpse but never cross. What lies beyond remains hidden, perhaps forever. But perhaps that is the essence of black holes. They remind us that knowledge is always partial, always reaching toward mystery. The whirlpool at the center of reality is both object and metaphor, both astrophysical fact and philosophical challenge. Science persists because the horizon resists. The sharper the tools become, the more refined the paradoxes grow. In this way, the study of black holes mirrors the nature of the universe itself, an endless pursuit, an ever-deepening mystery, a spiral without end. The whirlpool at the center of reality is more than an astronomical object. It is more than a collapsed star, more than gravity given absolute dominion. It is a mirror, a symbol, a question carved into spacetime itself. For in black holes, the universe whispers something unsettling. that the laws we hold as firm dissolve at the horizon, that truth itself bends inward, and that perhaps no knowledge is final. For millennia, humanity's quest has been to transform mystery into clarity. The sky once filled with gods became a vault of stars. The wandering light became planets. Gravity became law. Light became wave. Atoms became known. Yet in black holes, knowledge recoils. They are points where science confronts its own limits, where relativity predicts infinities, and quantum theory demands their undoing, where thermodynamics insists on entropy, yet information seems to vanish. Here, certainty breaks, and humility becomes the only language. Philosophers once asked whether the universe has an edge, whether time has a beginning. Today, physicists ask the same of singularities. Are they true endpoints or thresholds to something else? Is the collapse of matter into infinite density a flaw in theory, or a revelation of deeper laws still hidden? Some speculate that singularities are illusions, that quantum gravity smooths them into bridges, bounces, or seeds of new universes. Others hold that they are final horizons, not just for matter, but for meaning. The paradox is cut deeper still. If information can be lost in black holes, then quantum mechanics itself, the most successful theory in science, is incomplete. If information must be preserved, then black holes must somehow return what they take. Perhaps through Hawking radiation, perhaps encoded in subtle correlations, perhaps written on the event horizon itself. The holographic principle suggests that reality is not what it seems, that the three-dimensional universe may be a projection of data inscribed on distant surfaces. In this view, black holes are not aberrations but exemplars. Every horizon, a library, every shadow, a code. What does this say about reality? That space and time may be emergent, born not as absolutes, but as consequences of deeper structures. That matter and energy are not fundamental, but secondary to information. If so, black holes are not voids, they are archives, they are keepers of memory, preserving the past in forms we do not yet know how to read. For humanity, the resonance is profound. In myths across cultures, whirlpools were thresholds, passages to underworlds, doors to the unknown. In black holes, the metaphor has become literal. They are gates beyond which knowledge cannot follow. And yet, like all gates, they beckon. To peer at their horizons is to face our most intimate fears, that existence ends, that memory fades, that the self dissolves into nothing, but also to face our greatest hopes, that endings are beginnings, that beyond the dark lies renewal, that reality itself may be far stranger, far richer than imagination allows. Black holes remind us that we, too, are whirlpools. Each mind is an inward spiral, collapsing experiences into memory, memory into identity. Just as horizons hide singularities, so consciousness hides its core. The mystery of what lies within a black hole is mirrored by the mystery of what lies within awareness. Both are depths where inquiry falters, yet where meaning is born. On cosmic scales, black holes are sculptors. They regulate galaxies, ignite quasars, shape the stars that later forge the atoms of life. Without them, the Milky Way itself might not exist in its present form. In this sense, the whirlpools are not just destroyers, but creators. They erase, but they also give. They devour, but in doing so, they structure. Their paradox is ours, endings that sustain beginnings. Perhaps the most haunting thought is this, The fate of the universe may itself be bound to black holes. If the cosmos expands forever, galaxies will dim, stars will die, and only black holes will remain. Slowly, over unimaginable timescales, even they will evaporate, whispering their final quanta into the dark. In the far future, the last light may not be from stars, but from horizons dissolving. And when the last black hole fades, reality as we know it may end in silence, or perhaps not. Perhaps singularities are seeds. Perhaps each collapse births a new cosmos, a new expansion, a new sea of stars. In that case, black holes are not graves, but wombs, not prisons, but bridges. Then the whirlpool at the center of reality is not only the end of time, but the beginning of infinite times. Here the reflection turns inward, for what is the human response to such immensities? Or, yes, fear, perhaps. But most of all, wonder. The same wonder that led Einstein to imagine curved spacetime, Hawking to contemplate radiation. Thousands of scientists to stitch telescopes across the globe, detectors across continents, satellites across the heavens. It is wonder that drives humanity to seek horizons it cannot yet cross. The whirlpool at the center of reality is both real and symbolic. It reminds us that every theory is provisional, every law incomplete, every certainty temporary. That truth is not a fixed possession, but a horizon forever receding. In this way, black holes are not failures of knowledge, but guides to deeper knowledge. They do not end inquiry. They ensure it never ends. And so the closing image is this: a galaxy. Its stars drifting like embers in a cosmic tide, its center marked by a darkness we cannot penetrate. Around that darkness, light swirls, time bends, reality folds. From Earth, fragile beings of stardust raise instruments toward the void, listening for whispers, watching for shadows, daring to ask what lies beyond. The whirlpool at the center of reality is not only out there in the heart of galaxies. It is within. It is the pull of curiosity, the gravity of wonder, the collapse of ignorance into inquiry. It is the recognition that to be human is to orbit mystery, to be drawn toward the horizons we cannot escape, yet cannot resist. Perhaps, in the end, the singularity is not an abyss, but a mirror. Perhaps what collapses there is not only matter, but certainty, and perhaps what emerges is not destruction, but understanding, an understanding we have not yet learned to name. Until then, the whirlpool waits, silent, immense, inexhaustible, the center of reality and the center of awe.